Today I'll be going through the regression analysis, and I'll use regression model, which is a model that is in supervised. Is one of the models that are used in supervised machine learning category. So we are going to go through this regression analysis using the regression model. Um, I think I should share with you the dataset that I will be using. Let me just share that so that we can move together. Let me share the WhatsApp group. There is a file that I've shared in the WhatsApp group. You can download that. Oops. Just a minute. I think. Let me try to reshare again. Just a minute. So in the meantime, you can just open a new note. For those of us who are using Colab, you can open a new notebook. And you can just name it supervised learning, supervised machine learning, I mean. And for those of us who are using, is it VS Code? You can also open a new file and name it supervised machine learning. So let me share the file again. Yeah, I think you can now download it in your. You can download it in your from the WhatsApp group. It's called housing. You can check that. You can also load it in sample underscore data here. Let me just upload it. It's right here. So I'm hoping that everyone is able to upload this. Okay, I think you can just confirm if you're able to upload it. I don't want to leave someone behind. I don't get through with uploading. Who is through? Who has uploaded the data, the house in dataset? Winnie, have you uploaded the dataset? Bethwell, have you uploaded the dataset? Hey guys, have you uploaded the dataset? By show of hands, let me see. Let me see. Uh, Peter, can I mean uploading dataset in your whatever platform you're using, ID you're using. That is Colab, VS Code, or Jupyter Notebook. So, who has successfully uploaded the dataset before even I begin to write codes? I think Peter Kanyoi has managed. Any other person? Casey, you are so quiet nowadays. Have you managed to upload the dataset?
Just a minute.
Okay, I think I'm giving 2 minutes. Yvonne, are you able to upload the dataset?
I'm uploading it now. Just a minute.
Okay, okay, okay. What about the rest? David,
I'm uploading it.
oh, okay, okay. Oh, what about the rest? Akina Alice,
By the
Alice, have you
by
managed?
the way, yes, James.
Yes.
By the way, uh, mine is always like saying there's an error.
Uh-huh.
Actually, even the assignment part. Na imefanya hivyo pia sahi.
Which ID are you using? Colab, Jupyter, or VS Code?
Jupyter.
Using Jupyter. Can you use Colab today, and then maybe you will follow up after this lecture? Is that okay?
Okay.
Yeah. I think today everyone can use Colab. Then I'm hoping that now everyone has uploaded that dataset. So let us just get into um, so the data you have just uploaded is the data that has about is it about 7 columns, and those columns they just have information about houses that is in USA. Um, I just wanted I just want us to do just a simple regression analysis, and we are saying the regression analysis is a reliable method of identifying which variable have impact on a topic of interest. So the processing of performing a regression allows you to confidently determine which factors matters most, which factors can be ignored, and how these factors influence each other. So in our data, we will find some dependent variables and independent variables. Just to elaborate on that, dependent variables, these are main factors uh, that you are trying to understand or even predict. For instance, in this case, we have price as our dependent variable, or we have also independent variables. These are always factors that you hypothesize um, have an impact on dependent variables. So today, let us just check these housing dataset, and I think we're going to start by importing the dataset. Um, so I think by now everyone is able to import dataset. So let us just have import some libraries, that is NumPy, Pandas, Matplotlib, and Simple. So I think that is quite easy with most of us, right? I think you can just try to import. You import NumPy as NP, you import Pandas as PD, and Matplotlib.pyplot as PLT, and also Simple as CLS. In my case, I think I've already done that, so I'll just have to run this. So I'm hoping also from your end, you are able to import these libraries. It's just quite easy. I think any person who is facing some issues with the importation, I think we are good. You can just omit the import OS. You can just delete that. So after that, I'm just going to read this CSV file, and I'll just copy the path. So after importing libraries, you can load the data. That is by df, or you can just use the, let us just use data, or you can just call it housing data. You read that through this method from pandas, that is rigorous consistently. Then you just press your path. I think you can just check, after that you can check the nature of this data by using the head function. And I think I haven't, oops, I didn't run these libraries. So I should start by running these libraries, then loading the data. Then after that I can check the nature of these data sets by just viewing the first these really the data sets that are no. I think I sent you the wrong data set. Apologies for that. Let me send the, I think it should be housing underscore USA. Oops. Let me just set you the data set again. Let me stop sharing first. I have so many data sets that I think I shared the wrong one. Should be the USA housing. Let me share that. Yeah, it should be the one that I have sent. That is USA underscore housing. I think I can also, let me share my screen. Yeah, let me upload this. It should be the one for house USA underscore housing, this one. I think you can just change that. And let me just try and rerun this. Yeah, it should be this one. So just re-upload the dataset.
Excuse me, James.
Yes, please.
How comes your Google Colab interface looks different?
terms of what?
Mine is not arranged as yours, and I don't have those icons of changing them into tables.
Like this one.
Yeah.
Okay. Can you share your screen? We see what you have on your end.
Okay.
Yeah. Okay. The rest you can be uploading that
Now,
that data.
can you see my screen?
Yes, I'm able to see your screen.
It looks like this. And I don't have the icons that you have here.
All those I think you can just place your the cursor just below where you below what below your output. I think you can just can you try and place your yeah.
Here.
Yes, you'll see plus code plus text. You can just click that button to
This one plus code.
yeah, and then now you'll be able like to now divide your codes into snippets.
But how comes my data has been divided into 3 parts?
All three parts. Let me see that.
Yeah, like after this one here.
Yeah, there is no problem with that. I think is the screens that we're using because in my
Okay.
case I'm using large screen, so it depends, but it has no problem.
Okay.
Yeah. So I'm hoping the rest have been able to upload that. Let me okay. Let me resume representing. Okay. So I'm assuming that everyone is able to see this kind of data set. So we have like is it 7 columns? That is the average area income, the average area housage. We have the average area number of rooms, average area number of bedrooms, and area population, price, and address. This is the kind of data set that we that we have. You can also check uh, the information about this data set that is using the info method. So I just have to change this one to scene underscore oops, underscore data dot info just to check the information about this data set, so you can run that again. And in here, I'm told that my data set consists of around 5,000 entries. Um, we have also 7 columns with their data type being float 64 and one object. We are even told the memory usage for the dataset. It's using about 273.6 kilobytes. So I think these are some of the functions that we learned in the previous lectures. You can also like use the describe method again to just just to see some of the information, such as the mean. We have the count, we have the standard deviation max, we have the quartile, interquartile, and such information by use of describe. Let us just see that again. We have the count of each column. That is, each column, I think it has 500 records in all columns. We have the mean for area, income, we have the mean for area house age, the mean for area number of rooms, and you can see that is one. We have the mean number of bedrooms, have it 3.9, that is around 4 if we round up to the nearest whole number. The area of population, I think you can see some interesting information about this data set. You can also check the price. You can see the max price, you can see the minimum price. There is so much information that you get using this describe function. From there, I think you can just try to visualize these data. Let us just try and use this. That is data. Now we have a histogram here. Just to check on the price and count. We're able to see the number of houses. Let me just allow someone to join here. Yeah, I'm hoping that everyone is here. For those of us who are typing, I think I can give you 1 minute to try and visualize this.
James, can you scroll up a bit? Just a little bit. No, the first, no, the first upper part.
The first one, this one.
Yeah.
Okay. Are you through?
No.
Okay.
Yeah.
Yeah. You can also type this. Bedwell, Kamau.
Okay, I have a question. I can see you changed the data from the housing to USA housing.
Or to USA underscore housing.
Yes,
USA underscore
but now Yes, but now when I read your codes, I don't see that. I don't see USA housing.
It's just right above here. This is where I loaded my dataset.
Mhm.
Yes, I think I've indicated that dataset loaded.
So now I'm kind of lost because I don't know. Do I use housing data or US?
We're using USA underscore housing.csv file.
Right.
Yeah, I think you can change that. Any other question before we proceed? So in here we're just trying to create a distribution plot of this data, and you notice that I'm setting this KD to true. This KD just means it's kernel density estimation, and I'm just setting it to true. So I think most of us are just wondering what is the use of this KD stuff. It's just is a technique that is used to estimate probability density function of a uh, continuous random variable based on maybe a data sample. So you shouldn't be worried when you see the KD setting it to true. Um, what I'm interested in before even I get into the linear regression model, maybe I can just um, we can just try and find the correlation about these data variables, and even draw a heat map just to see to visualize the correlation between these data points. And how I achieve that is I'll use the heat map function. I think I can just divide these. Let me just divide these. Uh, data variables. I think I can just call it core, and then I just use the my data set here, which is housing data dot call. We have that function for just checking the correlation. And then what I'll just change here is I'll just pass the correlation here. Yes, I think you can just run this just to get the correlation matrix. And we have something here. that call is duplicated in future version, it will default to false. Okay, you can just ignore that, because by default it will lose all the numeric variables. It will just omit the other data types. I think you can now visualize that. Let me just use the CNS, that is the Synbone. The Synbone has a heat map function, and that heat map I'll just pass some arguments here. That is the my correlation matrix that is called. I'll just set the annotation to true, and then I'll just that is the column maps. I think after visualization I think even I can just use grains. Let me change this color to something different. Just to explain this, or what we mean this by this heat map. So we are starting from light green, showing that we have the list. Anywhere you see light green in this heat map, you just know that we have the least correlation of 0.0, or even maybe something that is almost equivalent to 0, something that is near to 0.0. So as we move upwards to 1, you just notice that we have 1 as the highest the highest value here, and it will show us that we have the highest correlation in these data variables. So anywhere you see 1, we have the highest correlation. So basically this means that we are starting from the least what the least levels of correlation in between the variables. So that is where we have this is what I mean by the CMAP. This CMAP column map, this stuff here, this bar here, that is just to help us to understand even this heat map better. So anywhere you see a green, that like in average area of income, where you have the highest correlation. We have also like where we have Z price, price. Anyway, you just see 1. You just know that we have the highest correlation, and that is the reason why we just draw this heat map, just to check to visualize the correlation between these variables. I think having understood our data set, we can just jump into just move to training our what? We can just move to training our linear regression model. And I want us to first split up our data into X array that contains the features of train on, and Y array with the target variable. In this case, our target variable is the price, and that is where we want just to split our data. That is that is on X. We'll have the train variables, and Y will be our target variable in this case. And how I do that, I'll just create a list that will contain all the other column names except for price. I just want the Y to be my price being my target variable. I'll just exclude it from the training variables, and that is why you can see that I have a df of area, that is avg of area income. I have avg area of houseage. I have avg area of number of rooms. I have avg area of number of rooms, and the area of population. So I have them in my x-axis, and I'll have my y is the price, because this is my target variable. If you check carefully, you notice that I have dropped the address column. I think you can see address. I think we had address in here. Let me just see. Oh, it's supposed to be. I had address somewhere. We have that is let me just look from the head here. So we had this column called address. You notice that column address will the address of where the house is located. It won't affect so much on the pricing, because we already have the area of we have what there is somewhere we have where is this? Let me just plug someone in. You notice that the address of a house will not affect what we are trying to do here. Can't affect what we are trying to achieve here. And again, I should change this one to housing underscore data. Should be housing underscore data. Let me change this. Underscore data. You can also omit the address in your case. I'm giving you 2 minutes to type this, and I can just paste it in, let me just try to paste this. I think you can check that in the in-call messages. I think that will be easier. You just copy paste that. So after we have splitted our data. I think I did mention SKLearn, but I think there is someone who asked that, and I gave resources on where to learn about these SKLearn library. And in these SKLearn libraries is where you are going to use model selection just to import the train test sprint. And these train test sprint will just enable us to divide our data into training dataset and also testing dataset. So again, you should check on the resources that I sent in the group so that you can at least learn these. What are the content of this library, especially now that we have begun learning about machine learning. So having imported these, that is train underscore test underscore sprint, I'll be able to split my data into 40-60%, whereby you see now I have X train, I have X test, I have Y train, and I have Y test. These are just variable names, and I'm equating them to. I'll now just use this train underscore test underscore sprint uh, to just assign my values here. That is the X and Y. And I'll also like specify the test size. I just need the test size to be 0.4 out of 1, so meaning that is around 40% of the whole dataset will be used for testing, and 60% will by default be used for training our model. I think having said that, I can just run this part, and I should get an error reason because I didn't run this. Yes, I should have run that first. So you notice that now I don't have an error after now I have imported this train underscore test underscore sprint, and even specified the size of the data that I want to be used in testing. You can just type this. Is there any question up to that point? I think that is it's clear. Get clear up to that point. So after like now specifying your test and train data, and even setting up the size of the test size, the test data size, we can now like import our linear regression model. And you notice that I'm importing this from sklearn dot linear model. I'm importing this linear regression model. So I think you can just from sklearn linear model import linear regression model, and you can create an instance of that linear regression model. You can just name it LM or what? Or you can just use the name of your choice, provided it makes sense. In this case, LM just means the linear model, but you can use the name of your choice, provided it makes sense. So you can just import linear regression model from sklearn dot linear model, and then create an instance of that model. I think I can just give you 2 minutes to type that. So I'll just run this. So by running that, I'll have imported my linear regression model. I'll have created an instance of that model, and I'll also have done what fitting. I'll have fitted my model with that's the X train and Y train data. So I think after that I can just print that is the intercept, that is the y-intercept. So are we together up to that point? So are we together up to that point? Thumbs up if we are together. Yeah, we are together with that is Devex, Devox, Omolo. Well, should I repeat that? Should I repeat that? Means are we together? Someone is asking me to send the sklearn code. Should I share that, or you guys you should type on your own so that you can get to understand these things? Let me just let me share this. Okay, I think I'm giving you 1 minute to type that. Yeah, I think most of us are through. But I think I can just try to explain what is fitting, and when I just invoke this the model, when I invoke this model, that is the linear regression, you notice that I am using this function, that is the lm.fit. Fitting just simply means that we are just checking how well a statistical model will represent data that is used to fit it. And there are various ways to do model fitting. We can, for instance, have residue analysis. We can have the coefficient of determination. We call it the R squared. We can also check the root mean squared error. We call it the RMSE. And we have the MAE, that is the root means, no, I mean the mean absolute error. And we also have something that we call the goodness of fit tests. So, but in this case, I just my interest is in the coefficient of determination, that is the R squared, and that is what we are going just to check. So after I have fitted my model with the X train and Y train, I think you have seen that I have just printed this intercept. That is lm dot intercept, and below here I'm just trying to do what, to just to put all the coefficient of determination, uh, that is lm dot coef underscore, just trying to put them in what, in a data frame, so that I can have them, like I want to have them represented in a table format, so that I can have the column names and the column now coefficient. So I think I can just achieve that by invoking this lm.coef underscore, and in here I just want to take x dot columns, and also in columns I just want to have that header for that is coef. What I have here, I think I can just rerun this so that you guys you can see that. So in here I'm having these x dot columns. These are the column names, and I have also the values for the lm dot coef in this column. So I'll explain everything here, what it means by some of these values. So let us just begin to interpret these. We are saying that holding all the features fixed, this means that 1 unit increase in one unit increase in avg.area income will be associated with an increase of the price by this amount, that is 21.52 US dollars. So and also we have let us just check these features and how they influence the pricing. So we are saying with just 1 unit increase in average area income, it will just cause an increase of the house price by 21.52 US dollars. So I think we can also check the other features, such as that is the average area of houses. You can also check the average area of house number and how they influence the costing of these housing. So these are just prediction. Now simply that these are just predictions of how maybe a certain variable could affect the pricing of a house maybe in future. We have what? We have a feature like avg.area number of rooms is associated with an increase of what? Of around these 122,368.67 US dollars. So you notice that all these features, in one way or the other, they will influence the price of the housing in future by these values that we are getting in here. I think you can just try to run this. You can just try to test this. And I'll just have a variable prediction, and I'll invoke now my model, that is the linear model dot predict, and I'll just pass the test data, that is x underscore test. It even tried to present that in a scatter plot. I think you guys by now you should be able to draw scatter. So let us just see whatever you have explained here in a scatter plot. So this is the visualization of what you have just explained. You have just explained. So when we train out to test our model with this test data, this is the kind of of scatter plot that we are getting. Um, you notice that it's kind of a straight line. I don't know if you guys have noticed that. If I were to draw a line here, you notice that every data point is will be close to that line. I don't know if you guys have noticed that. But you should. You should have noticed that. So this one is we should use this plot. Let me just try to run this. I'm hoping that you guys you're able to follow up to that point. And I'm waiting for any question, maybe from what we have visualized here. Any question up to that point? Before we get into metrics of regression evaluation. Any question, Alvin? Alvin, I think you had done something like you said that you had developed some models. Is Alvin with us? I think Alvin has not joined. Any question so far? If no question, I think we can just get into regression evaluation metrics. And in here, I just want to check I think I had said this, so something about the mean absolute error and also the mean squared error and something we call root mean squared error. So to start with mean absolute error, this is the mean of absolute values of errors, and I think most of us in here have done statistics. You should be familiar with MAE, and you know it measures the average absolute difference between the predicted values and the actual values. And I'm aware that you guys you have done this. It's less sensitive to outliers. I think by now everyone should be able to know what are outliers in datasets compared to the mean squared error. So again, mean squared error is the average of squares of errors between the predicted values and the actual values. And you notice that mean squared error is the MAE squared. These are the formulas. I don't think I have to explain these equations. You guys, you must be knowing what they mean. Root mean squared error, that is the square root of the mean of squared error. Is the square root of now this the mean squared error, and we are told that is the square root of the mean of the squared errors, providing a measure of average magnitude of errors. Is the same as unit as the target variable, making it easier to interpret. I think these are things that you have gone through, and I just want to show you how you can check all these now using our model here. So I think you can just check the MAE. It's quite easy because we're just going to use the matrix in sklearn. So we just use the matrix, and we invoke that method for mean absolute error, and then this is going to pass our y-test, and prediction. Then we should be able to get the mean absolute error. When I run these, you notice that I'll get all these values. That's the mean absolute error, the mean squared error, the root mean squared error. So let me just run this. You notice that I'm just passing for the mean absolute error, I'm just passing the y-test and the prediction. Yeah, but I'm using different formulas here. That is matrix.mean underscore squared underscore error, and then I pass my arguments here. So let me just try to run these, and you notice this is the values that I'm getting for MAE, MSE, and RMSE. So I don't know if there is any question up to that point, but this is how we implement the that is linear regression model. It's just quite easy. Initially we were programming the whole stuff, but now we can import that from sklearn. So any question up to that point, or you guys you're just hanging? Any question? Winnie?
Yes, James?
Do you have any question concerning the...
No, I don't. I'll have to redo from your notes. Yeah.
Was I very fast? Or...
No, it's always good to also go through the notes to just ndio ishike vizuri.
Okay.
Yeah.
What about the rest? Bethwell, have you understood that?
I also think I'll have to maybe watch the video. Okay, I hope you are recording. I'll have to watch again and do it because right now I'm getting errors.
You're errors on your end? Let
Yeah,
me
me
know.
too. Me too. I'm getting errors. So yeah.
Where are you guys getting errors? Like in your case, Winnie?
James, I'm embarrassed to share my screen.
Okay. No problem. You just take your time to check through the codes. But these are just quite easy snippets to run. So any questions so far? Brianna? Brianna, are you able to follow what we are doing here? Let me see. Sharon Nyamoya, are you able to follow? Sharon? I think, I don't know if Sharon can hear us, but I'm hoping she's following. So any question from what we have covered? I don't know if I can. I don't know if we have enough time to check another example of regression model. Uh, let me just check. I think I had another example. Okay, let me just share another regression model here. Yeah, let me just share my screen. Yeah, I have another example here for Boston house price prediction. And again, you're going to use the linear regression model just to predict to predict, oh, someone is asking for the formulas. Let me just share the formulas because someone is asking for the formulas for calculating the what that is FAEMSA and RMSE. Let me just share that. Um, I'm very close to that tab. Let me just share that. in the in-call messages. You're just going to do an import of these metrics. Let me share the whole snippet. Yeah, I think I've shared that. Let me open another example here. We are going to predict the price of houses in Boston. So this is the problem statement here, and we are saying the problem that we are going to solve here is that given a set of features that describes a house in Boston, our machine learning model must predict the house price. So to train our ML model with Boston housing data, we are going to use the skitlands Boston dataset. So again, we are going to start by importing libraries. That is pandas, numpy, scalar, matplotlib. That is Seaborn, and also in this case, I think we are going to use the matplotlib inline. I think I can just omit that for a second. So let us just begin by importing the Boston dataset here. Let me allow someone here. Let me, yeah. So I'm hoping that you guys have imported these libraries. In fact, you can just copy from the previous code and paste in your new tab. So after importing these libraries, you're going to import the Boston housing dataset. I think I can just begin by running this snippet here. But I'm expecting a lot of errors from these snippets. I think we are through with importing of libraries. So let us just get into importing this data. And the sklan.datasets have these as this dataset, but I don't know if it will apply here because I think this code I wrote it in at cargo. But let us just check and see. Yeah, I think we have a problem here. We are told that the Boston housing prices dataset has an ethical problem. The author of this dataset engineered a non-invertible variable. We assume that I think you can use other methods of importing this data. I think they are given us the URL here. I think you can just copy this snippet here. I knew we could lead into some issues here. Let me just try to import this again. I think I can use this URL here. I think I can also share this. Let me share this snippet over here. So I think I can explain this. The first line of code is about what the data URL. I think you can see it. This is the source of our data set. The second one is you're just trying uh, to read. You notice that this one is just we have just assigned a variable to our variable to our I mean to our to be hold our URL data. So again, we'll have to read this using the pd dot read underscore csv. Then you just pass in your URL. You want to separate this with some space. You want to skip rows, and I think you can just omit this. And so to initialize the data frame here, I think you can just pass in data because now our data is in this data variable here. So let us just begin by running this. Oops. I will read that all the input array dimension except for the concatenation access must match exactly. You can do away with that and just check what my row.df.head has. Yeah, I think we should return this. That is headers none. Just that is header none. This is because when you omit this header none, your first row will be treated as the header. I think you have seen here that we're using our first row of data as header, and we don't want that. So I think you can just try to rerun this, and you notice now I don't have issues. Let me try to initialize this dataset of mine and even try to see the head of this dataset. You notice that now my I have this dataset here, and I have my columns named using indexes, that is from 0 to 12. Yeah, to 12. So this is quite different from what we had initially, because You notice that in here now we don't have these the names of the columns. So again, we are going to check how to add column names in this dataset, because understand that we have those column names just below here. So our next thing will be to, after you guys you're able to import this Boston house in dataset, and even initializing this data frame, and even able to see the head of that dataset. The next thing that you're going to do is naming all these columns. I think by now, I think by now you should be able to name these columns. But I can give you 2 minutes to just to import that data, and even initialize it to initialize the data frame, and even try to see if you have access for that data set before we get to naming that data set. So 2 minutes for that. So are we together up to that point? I think by now you should be able to access that data set. Uh, Let me just add. Yeah, I think it's just right here. Let me add a code here. Features name. We are going to have a list of features name here. Features underscore names. I think you can. We can use these names here. That is the yeah, the cream. Let me just try to type this very fast. is cream. The second column is zin. The other one will be Indus. The other one is what? Is it Chas? The other one is Nox. Rem. H. We have this for weight distance something. Oh, we have also RAD. Oh, we have the tax. And let me check the other one. That is, I can copy this. Paste it here. The other one is link up to here. Copy. And the other one is link this. How many words are these? 1, 2, 3, 4, 5, 6, 7, 8. I think 12. That is 1, 2, 3, 6. There are 13. There are 13 of them. So after that, we can add the feature names to the data frame. We're just going to invoke that is our data dot columns, and then we set them to I think this one will also be data. Let us say this. Oops. Just like that. Now this one is feature names. Now you notice that now we have I think I can just share with you this. I think you can use that to give your data set a header. You notice that now I have my data set is having a header. You can easily read this, and we have this explanation on that is cream per capita. That is capita crime rate by town. We have Zen for that is proportion of residential land zone for lots of that is 25,000 square feet. We have non-retail business acres per town, and also the rest. So after just adding the features, I think we're just going to move to the next thing, and that is adding target variable to our data frame. And in and just use the, I think, data.target. Let me just check. Oops, why am I getting this? That is data frame object has no attribute target. Where are we getting this? I think you can just try to check if we have added that. Let us just check this by using our data.head. Let me just try to run this again. I think I've added the price. That is the price column. That is what I was just checking. I think I can also check the shape for this. That is 506. That is 506. That is 506 rows and 14 columns. You notice that initially we had 13 columns, and now we have added an extra column. That is the price, and we're equating it to that is our target. That is our target column. You can also try to check the columns, and you notice that this price is included also. You can also check the data types for these. You notice all of these are float variables. Let us just try to identify the unique number of values in the data set. We achieve that by using the n unique, that n for numbers, and unique function. Maybe you can just run these and just see the unique values in our data set. You notice that in each and every column we have a unique value. We have some unique values here, like in the price we have 229. We have in the age we have 356. We have the just, I don't know. I think this data is explained. These names are explained here. We have Charles river dam variable. That is one if track about river. I don't know what is the meaning of this because I don't know what is the meaning of this, but one if track about river. Oh yeah, I think this one is just checking the just river dam variable, or checking maybe if is it we have a river, because one if what one if track about river. I think this data set was just a confused one, but we're just going to use it. We have the weighted distances to 5 Boston employment centers. We have the RAD, that is index of accessibility to radio highways. I think that makes sense. We have the tax, that is full value property tax rate per. So that will make sense. We have the P ratio, that is pupil teacher ratio by town. Okay, I think these columns are making some sense. Lower status of population. And also this one is, we are given this one in form of percentage. I think most of them are making sense. That is that is proportion of non-retail business acres per town. I think some of these columns are making sense. I think you can you can also try to describe this data. You get more information about this data. You check the mean, the count per column. You can check the max value in each column. In all the 14 columns here, we have the max value is 50 bob. That is 50.0000. I'm assuming that this price in terms of millions, we should have indicated that 25, we have 21.17, the lowest being that is 9, the minimum being 9. I think what we can do, we can check the correlation between the fixtures by using the call function, and we can assign that to, that is the correlation variable. Let me just comment out this and run this. We can check the correlation matrix. You can check the shape of the correlation matrix. Where we are getting it is a 14 by 14 matrix. After that, I think we can get into checking the heat map. Let us just try to visualize these. Check the correlation here, and I notice that since I have 14 columns, that is I mean 14 by 14 matrix. I think I should resize my my correlation figure here, and that is where I'm just trying to enlarge these by using the fig size. I'm using a 20 by 20 size, and then just invoking the this heat map function. Again, I'll just pass the correlation matrix. I set the C bars to true, the square to true. I also need the format to be the format for the values inside these heat map plot. I want them to have just one decimal place. That is why I'm using this format FMT. Setting it to in quotes, that is .1f. I'm also setting a notation to true. You notice that also here they have something different, that is r0_kws. This one will help us to at least customize our what that is features such as or attributes such as font size, and in this case I've used a font size of 15, and also I'm setting my colors as greens. So I think I can just try to run these and see the kind of picture that we are going to get. You notice that this one is a bit large compared to the one we had. Simply because it is a 20 by, I think I can just reduce this one to 15. Just reduce this one to 15 so that it can fit in my screen. I think this one is a bit large. Let me use 10 by 10. I think this one will make sense to us. So again, the correlation starts from, in this case, we have even negative correlation. You notice that there are some variables that have negative correlation, meaning that they don't relate at all. And in this case, they are represented by negatives. And the color is light green. So where you see light green, you must have a negative value. But again, you see the ones that have 1.1, they have the highest correlation. I think from there we can just try to sprint target variable and the dependent variables. And in this case, my x variables will be all the data columns, dropping the price. That is why I'm using data dot drop, and then I'm just dropping the price column and using that column in the y-axis. So I think I just have to run this. And you notice I don't have an error. Again, you're going to repeat what we did with the previous model. You sprint the training and testing data again. I think I can just run this. And then just try to train our model. Shouldn't take long because we don't have much data here. Here we are converting the coefficient values to a data frame. I think we did that even with the previous model. That is the attributed the coefficient. Let's just carry out a model prediction on trained data here. I think by now you should understand we have the MAE, MSA, and RMSC. Now these are values again. This R squared is a measure of linear relationship between x and y, and you notice it is almost it's 0.7. So you're just checking the relationship between the y and x values. So we say that it is interpreted as a proportion of the variance in the independent variables that is predictable from the independent variables. We have the adjusted R squared, and this compares the explanatory power of regression models that contains different numbers of predictors. I'll share with you these five so that you can go through this. And I think what we are left with is just visualization of the differences between the actual prices and the predicted values. Let us just visualize these. And you notice in this case that we don't have a straight line. You notice that we have, if we were to draw a line here, you notice that there are some data points that are very far away from our line here. So you notice that, and this is affected by, can be affected by, you notice that we are using very small data set of around 544 544 what? 544, is it, was it 544? Let me just confirm that. I think there is where I checked the shape of, I think I can still check the shape here. I think I should get the shape for this. Yeah, it was 506. It was 506. Was 506. It had 506 rows, and that is where you can see we have some data points away from the center here, from this straight line. If you were to draw a straight line here, but if we added maybe some, or maybe used a larger data set, we could have the actual prices almost similar to the predicted prices. But in this case, but again, this one is, it isn't that bad. Um, but if we could have a large data set, you could have seen that we have you could have maybe these data points forming a straight line just from the origin here. I think with that, you notice that even you are saying that there is no pattern visible in the plot, and values are distributed equally around 0, and we say that the linearity assumption is satisfied, but it isn't quite satisfied, in as much we don't have that straight, this data point forming a straight line here, like the one we had before. I think we can just check the normality of errors. Just check and in this case I should change this one to this plot. We have no difference with the previous meaning, with the previous histogram here. But by that, this is exactly what we should have. Only that in here we missed some data points. You can see like this one is very far away from other data points. I think you can let us just check this predicting the test data with the model, and we can check these the model evaluation here again, so that we can get the adjusted R squared, we can get the R squared, you can have the MAE, MSC, and RMSC. I think these are they are quite fine, but if we had a large data set, you could have seen these reduced. Even some values that are maybe less than 3 here could have maybe a value less than 5 here, based on the size of data set. But that is all about linear regression model, and I'll share with you these examples. But you notice even I have also tried to check other models, that is the random forest regressor model. You can go through this code. I have also XGBoost regressor. I think we checked these in the theory part. I've tried to even implement the SVM regressor. But we'll check them at your own time. But that is it with a linear regression model. That is an example of supervised machine learning. So tomorrow we are going to check unsupervised machine learning. And even touch some reinforcement learning. So any question on that? I think I'll just have to share these files with you so that you can check them. And if you get any question, you can maybe share. You can share with me. Any question? Any question? Casey, have you understood that?
I'm okay.
You okay? So I think I'll just have to I'll have to share those files with you. And if you come across something you can't understand, you can just reach out. Yeah. So if no question, I think we can just drop. Or yeah, I wish you guys a good night. See you tomorrow.